Yeah, yeah. I will try to record your talk.
Okay, so I don't think that we're going to go too much into detail on every aspect of this problem because some of it's just like some some calculations and looking things up from data tables and whatever. But so here's the basic setup for the problem. It's just like what we had in that figure at the end of chapter 18, where the pion decays into two photons, and so we're given the energy of the pion in GeV, and we say that okay, well the pion flight direction starts along the x-axis, and obviously the decay into two photons will be in a plane. So let's just pick that it's in the xy plane. Um, so let's see. Let's just start with part B here. So given that the pion has energy like 0.75 GeV, we want to calculate beta. And so as we saw in that chapter,
Sorry, one moment. I just wanted to say that uh, I want to form like to visualize everything. So basically, that's the same picture we had in the book, right?
precisely, yeah.
hmm But in this case, our pion it flies along the x-axis instead, right?
Yeah, and then the plane that is sort of like spanned by the two photon directions, we're just going to call that the xy plane,
Uh
just so
huh.
that we don't have to deal with the z coordinate.
Yeah. Okay. 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 Thanks.
So yeah, the first thing that we're going to do is actually find the velocity of the pion, but in the lab frame, not in the pion frame. So to do this, we're going to use one of the formulas that Penrose gave us, where the energy is just gamma times the invariant mass. Um, so is this step clear here, like where I'm starting?
I'm not sure that I remember that formula with gamma and mass.
Yeah, let me see if I can pull it up real quick.
Oh, you are working in the units where c equals to one, right?
Always.
Yeah, yeah, and that's why I was a bit confused. Yeah, okay.
Natural units for the win.
Definitely. So yeah, the equation that I'm using is on page 436 in chapter 18.7. So it just says like, oh well, maybe it's not. I don't know. I think I may be taking an extra step there, but either way, the energy is the mass in natural units, and that would just be like gamma times the rest mass. Um,
Yeah, I see that formula, but it's kind of so on page 436 we have the formula for the mass, which is exactly the same, like gamma producted on the rest mass.
yeah, so m there is actually like the energy, right? And then mu is the invariant mass or the rest mass.
Yeah, yeah, yeah.
So I just used the same equation but slightly different symbols,
Yeah, got it.
right?
Yeah.
So when I'm saying m pi here, like I'm talking about the invariant mass of the pion. And when I say e pi, I'm saying that's like what's given up at the top of the problem. So I'm just using this equation like E equals gamma m. And then, so this equation can pretty easily be solved for beta. You just like square both sides and then isolate beta. So we get that this thing's moving pretty fast, like 98.4% the speed of light.
Yeah, it's interesting that
So this is
that you can deduce the velocity from the energy.
yeah, it's kind of interesting. I mean, so the reason is because we're talking about like in the lab frame.
Mm-hmm.
In its rest frame, it's just going to have like the mass of the pion. So we wouldn't be able to find gamma in the pion rest frame. We could find it in the lab frame. But yeah, so this thing's moving pretty fast, about 98% the speed of light, and so we're told that in the rest frame of the pion, then the angle that one of the photon makes with the x-axis is 45 degrees. So we're asked, well, what does this angle look like in the lab frame? And the way that I go about solving this is I do like an inverse Lorentz transform just on the like the zeroth component of 4 momentum, right? Like this would be like P0 in the lab frame. And so you just do like gamma times P0 in the rest frame. And then this right here, this is a plus because we're doing an inverse Lorentz transformation, right? So beta would go to minus beta.
Yeah, may I ask you once again about this x apostrophe axis? What is it?
So the primed is usually, I think, at least within this problem, the primed is talking about like the pion rest frame.
Mm-hmm, mm-hmm.
So like theta 1 prime is in the pion rest frame.
So in like from the point of view of the pion, the photon is emitted at the angle of 45 degrees.
Yeah, exactly. And then so what we need to do is do a Lorentz transformation to write out like what this angle could be in the lab frame. So to do that, I just start by getting the energy in the lab frame, which is given by an inverse Lorentz transformation on the 4 momentum of the pion in its rest frame. And then, let's see. Yeah, E rest.
So you've taken only the first part of this inverse Lorentz transformation, right? Only for the energy thing.
Yes, exactly. Yeah, because the P lab, we're given the magnitude of that.
Mm-hmm, mm-hmm.
So the when I say E rest here, this is the energy of one of the photons, right? And so it's basically in the rest frame. Maybe it's best to draw this out. Just a moment. Trying to connect my iPad here.
Yeah, okay.
Okay, can you see OneNote now?
Mm-hmm.
Okay, so like in the Pion, in its rest frame, you know, if we see like the first photon going off at an angle 45 degrees, because the pion is like not moving in its rest frame, you know, sort of by definition, then the second photon must go off in the same direction, or like opposite direction. See what I did there?
Yeah, just like a symmetric argument.
Yeah, it's just because, like, if you want to conserve momentum, you know, the initial must be equal to the final, right? And the initial is 0, and so the final is P1 plus P2, so P1 is equal to minus P2. So this is what it looks like in the rest frame. And then if you want to do it in the lab frame, then you have like the pion coming in, and then it decays into 2 photons. And so what we're wondering is, what is theta lab? That's what we're trying to figure out.
Yeah, for example, if we need to catch somehow, like maybe reflect the photon, right? Like where to place the mirror.
I'm not sure what you mean.
I mean that probably like we need to know that angle, like maybe for some experiment, because the angle will not coincide with the rest frame. It will be deformed because of the large speeds.
Right, yeah, so I believe that theta lab will actually be smaller than theta rest. Right, this is theta rest. Okay, so I can switch back now. I'll switch back and forth when I'm drawing.
Yeah.
Okay, so in the rest frame, since the momenta have to cancel out, the energy of each photon is just half the energy of the pion in the rest frame, right? So the energy of the pion in its rest frame, you know, it's got no momentum in its rest frame, so the energy of the pion is just the mass of the pion, the invariant mass. And then if you want to talk about the x component of the momentum of the photon in the rest frame, then what you need to do is just take the magnitude of it and project it onto the x-axis using cosine of theta rest, right? So theta rest is 45 degrees, and we're just projecting it onto the x-axis, or projecting the momentum onto the x-axis to get this term here. So now that we have the momentum of the first photon along the x direction, we can plug this into this inverse Lorentz transformation expression that I have up here. So I just straight up plugged it in, right? We got yeah. So plugging everything in, we end up with the energy in the lab frame in terms of, you know, theta in the rest frame. So you can factor out a mass of the pion and a gamma, because this E rest is still a half times the mass of the pion. You know, there's a lot of substitution going on here, right? We all of these things are just starting with this first expression, and then I'm finding, using the physical intuition of what's going on in the rest frame, I'm finding out how to substitute these values, right? So I find E rest, and I find PX rest, and I plug these in.
And you are also using that, this P rest X will be equal to E rest, right? Because I'm seeing that you are, when going from, you have these 3 formulas starting with E rest and ending with E lab, right?
Right.
And I see that uh, after substitution into the first equation, you can kind of you're using this module like absolute value of p rest is equal to 1/2 of mass of the pion.
Yeah, and so that's because we're just talking about for one photon, right? We're talking about like the gamma 1, the first photon or whatever. The one that's making a 45-degree angle with the axis.
So basically,
we're not talking.
it's because of this angle, right? Like that's why both of the photons will have the same energy.
Right, yeah, because in the rest frame, they have to be going opposite directions from each other. And the energy of them must add up to the energy of the pion in the rest frame. But the energy of the pion in the rest frame is just the mass of the pion.
Yeah, the question is, could it be divided like unevenly?
Yeah, I also thought about that before as well.
Not in the rest frame. Because you have to picture just like a particle sitting at rest at the origin and decaying into two particles.
Mm-hmm.
And you must consider that the energy is conserved and the momentum is conserved. And so if only one of those things were conserved, then yes, they could be split up unevenly. However, the requirement that both are conserved means that the momenta have to be in different directions. Or, I'm sorry, the exact opposite direction.
Mm-hmm. I just was thinking about like a more maybe more general situation, like for the different angles, like maybe not 45 degrees. In that case, it seems to me that those momentums for the two photons, they will have something like this sine cosine dependency. I mean that one equation will be this absolute value produced by cosine, another one will be the same thing but with like multiplied by the sine. So we will have like the same overall momentum.
Well, so okay, I think the thing that you're pointing out here is that in the rest frame, it should be emitted uniformly, right? Like there shouldn't be a preferred direction that one of the photons goes in the rest frame. And I agree with that. And all I'm saying is that like when you impose conservation of energy and momentum, then it requires that those photons are in exactly the opposite direction. It doesn't matter what theta rest is, but if the first photon is at theta rest, the second photon will be at theta rest plus pi.
Yeah, of course.
Yeah, so that's just like imposing conservation of for momentum, or in other words, conservation of energy and momentum. So, yes, I guess I could have written out that step. Maybe I'll rewrite it and add it. But yeah, so I put the magnitude of P rest for this first photon is just E rest. So, and then I substitute in what the E rest is, and I can end up factoring out a like 1/2 m pi. So ultimately, I end up with this expression for the energy of that photon in the lab frame in terms of cosine theta rest.
So this is more of a general question out of the scope of this, but say that it was divided into two different particles, decayed into two different particles, would the angles then be different? Could we know anything about this?
Yeah, actually, I do have another problem that's very similar. It's charged pion decay, where the like. Here, I can write this out.
I mean that they wouldn't be the same from each resulting particle, that they would not be the exact same angle relative to each other. Just to be clear.
Yeah, so you're talking about, like, so here's the example that I'm going with where they would be different angles. Is the the negatively charged pion goes to like a muon and anti-muon neutrino and a photon, right? So this is a more complicated interaction for sure, but it looks something like this, where you have like a pion coming in, something happens in the middle, and then you have like a muon, you got a muon neutrino, and then you got a photon. So this is a case where in the rest frame, when you draw it out, it would be like, so the pi minus is just sitting at the center, and it's like, okay, so maybe it emits a muon in this direction, and maybe the photon in this direction and the neutrino in this direction. It's a little floppy, but do you see how I drew this here? It's applying the same conditions. It's that like the sum of the momenta beforehand must be equal to the momentum after. You know, and this could be like the 3 momentum or the 4 momentum.
It's also interesting to see that I guess the angles are always symmetric.
Like there is a dependency. There is a dependency, some kind of the dependency, or like because maybe there is a dependency on those angles, like the masses of the particles and the overall momentum, something like that.
All of these angles in the rest frame are determined by the conservation of 4 momentum. Like it's just, yeah, you got to make sure the energies add up and that the momenta add up, and it should be equal to the initial.
And you know this, but this is how we identify different kinds of particles in particle accelerators, by these angles, or?
Well, I mean that is a really good question. Like basically what we'd end up with is like for this interaction with the pi minus decaying into 3 different particles, we have detectors that'll pick up a photon. You know, these are just like what you have on your phone, really. It's like the charge coupled devices, and we have detectors that'll that will find muons. You know, these leave a pretty strong signal in these things called silicon pixel detectors, where it basically will look for a charged particle that is passing through the material and ionizing enough stuff to let a current pass through. So basically, like what we'll see...
digital camera.
I'm sorry?
Like a CMOS sensor in a digital camera or something, it sounds like what you're describing.
Well, you're definitely right that the CMOS is how we would detect the photon, right? Or some sort of photomultiplier coupled to a CMOS. But the way that we would detect the muon is like if it's passing through like some, you know, crystalline structure, right? I'll just draw something. Then like, let's say that the muon takes this path, right? It passes on through. Well, you'll see an ionization path, like, oh, this particle is ionized, this one was ionized, this one was ionized, this one was ionized. And you can pick that up with currents.
Cool.
So that, like, this thing that I have on the right is how we would detect the muon. But, so the thing is, we would detect the photon and the muon, but we don't have anything that would detect this neutrino. So what you would do is actually, like, you'd have your values in the lab frame. You know, the lab is like the Large Hadron Collider or something like that. So you have your measured values from your detectors, and what you would see is that the momenta don't add up precisely. Like what we would see is something like this in this bottom graph, where they're not directly opposed to each other. And so what we say is like, oh, well, there must be just like a missing track in this direction.
So we infer that it has to be there because it has to be symmetrical.
Yep. And so that's just because we're asserting that this conservation of form momentum holds. So yeah, I think you're exactly right with that intuition of saying like we could actually detect these particles just using conservation of form momentum. You know, we use some cool tech to find the photon and the muon, but we need to sort of mathematically infer the presence of the neutral particle or the light neutrino. You know, we need to infer that presence.
Since
just
it's
from,
not charged.
Yeah, it's not charged, it's moving very quickly, and it basically interacts only through the weak interaction, which we haven't talked about too much, but effectively it's like it doesn't interact with much, is probably the best way to say it. But yeah, so I think this is a bit complicated. You know, I would like to continue with this example here.
Yeah, it was kind of a detour. I hope people don't mind too much.
Yeah, but it is nice to see like more complicated stuff in the basic terms. So it's really nice.
Definitely. Yeah, I mean, at some point here, once we actually get into like particle physics stuff, I would love to talk a little bit more about like stuff at CERN and you know, experiments and everything.
Yeah.
Have you guys tried to experiment with cloud chamber or bubble chambers?
I had a professor that built a coffee table cloud chamber.
Mm-hmm.
Yeah, it's not that hard actually. You can do it with like an alcohol vapor and see the trajectories through the vapor, the particles.
Mm-hmm.
It's interesting.
Surprisingly easy.
I never thought about like doing a DIY project with it, like cloud chamber.
Yeah, I actually did it 1 year ago, and I just tried to find out videos what I tried to record with their cloud chamber. But yeah, it's very nice ways to demonstrate how their particles can interact and decay and go to the different directions. It would be really nice to have that at a live show and comment what happens in the chamber.
Like a cloud chamber stream, something like that on Twitch.
Yeah.
That's pretty cool. So let's see. Does this stuff that I have written down make sense with like why conservation of form momentum would mean that like independent of whatever theta rest is, that the you know the angle that the second photon makes would just be like pi minus that?
Yeah, it seems so. Yeah, like of course you can write more formulas, but I kind of believe you because it's nice.
Yeah, so this only works because we're in the rest frame of the pion, and there's no preferred direction when the thing's at rest.
Yeah, so
right?
basically every pion decay is the same from his point of view, except like of the rotation of the whole system. So
Right, yeah. So there's some sort of like, you know, it doesn't worry about yeah, so I guess what I'm saying is that it's not going to go off in different directions in the rest frame. It's only going to be collinear in the rest frame, which is not the case in the lab frame, right? In the lab frame, it would be kind of difficult to see like a photon going off in the other direction, right? Because then this would have to be a very high energy photon.
mm-hmm.
Maybe we can get back to that.
Okay, let's go back to the formulas.
All right. Using these expressions for the energy of the photon in the rest frame and the momentum of the photon in the rest frame, we can substitute these back into our Lorentz transformation and find out that the energy of the photon in the lab frame can be given by this pretty simple expression where, if you notice, now we actually know all of these values. Like, you can go look up the mass of the pion in the particle data booklet, and we know gamma because we know beta. We solved for this before, and so beta again is here. So the only term that we have to worry about when considering the energy in the lab frame is theta rest. So what we can do is write theta. Maybe I need to give some motivation here, right? We're trying to find the angle in the lab frame for the first photon. So the way that I do that is by taking like an inverse tangent of the angle.
Sorry, one more question. So this primed theta is theta rest, right?
Correct. Yeah, and then the unprimed coordinates are the lab coordinates.
Mm-hmm. Yeah, okay.
But I actually dislike working with the primes and unprimed, so I prefer to actually label it lab and rest. So the angle theta in the lab is just going to be, like what you would normally think of as like, your standard picture of the tangent, right? The opposite over the adjacent. So we've got the y component of the momentum in the lab over the x component of the momentum in the lab.
So it's just like a right triangle.
Exactly. And so, we get similar expressions to this here. And what we end up with is like some things cancel, and we can actually write tan theta lab in terms of tan theta rest. You see, I end up with this expression using the betas. So this ends up being like...
It seems that's the right moment to use the second part of the Lorentz transformation, right? Like the part for the momentums.
Correct. Yep. Yeah, so this is where we would use the fact that it's in like the XY plane. The P lab will be the inverse Lorentz transformation of P rest. So we'll get a very equivalent description as up here.
Yeah, and we will have the similar cosines and sines as in the second equation. P rest x.
Precisely, yeah. And so ultimately, I did a couple of the steps kind of implicitly here, but you're right. So you do the Lorentz transformation on this, and we get it. Like the y component would just have the sine on there, and the x component has the cosine. So once we do this inverse Lorentz transformation, what we end up with is like 1 over gamma beta times the tangent of theta rest to get the tangent of theta lab. So here, we can actually calculate it, right? Because we know theta rest, it's given as 45 degrees, and we know beta, which we calculated. So I just went ahead and substituted in those values. I guess I should convert this to degrees, huh? 0.18 radians.
Mm-hmm. Yeah, so we obtained the angle. Yeah.
Can you explain when usually the Lorentz transformation is said to preserve the angles, how this actually fits to this? There must be explanation of how because here the angle is different on left frame and left frame.
So you're saying how does the Lorentz transformation change what the angle between the two photons are?
Yes, and relative to the common statement that the Lorentz transformation should maintain angle. There's probably something I just it doesn't just match in my head, but.
Well, so the relation that we just came to was that the tangent of theta in the lab will be 1 over gamma beta tangent in the rest frame. That's the expression that we just got to. And the way that we got there was saying that like tangent of theta lab is just going to be the y component of the momentum in the lab over the x component of the momentum in the lab. And similar to what we did before, the y component in the lab will be gamma times py rest wait, maybe that's not right. I think we need an energy term in there too.
I kinda how to say that, like roughly calculated the value in degrees instead of the radians, and it looks like it's like 11 degrees.
Yeah, so I mean, this is sort of what we expect if we go back to my drawing up here, right? Even though that in the rest frame it's 45, since the pion is actually moving, we would think that this would actually get like a pushed toward the x-axis
Because of the high speed, yeah.
Yeah, and it's like, I mean, I think this is where the visualizations from Chris's videos come in well, right? Like if you look at the space-time diagram, it sort of closes in on itself as you go to higher and higher speeds.
Like scissors.
Yeah, so like, you know, the angle between these two photons, it decreases when you apply the boost.
Yeah, true.
Okay, I had a it was on my side a misunderstanding. It is said that the distance is invariant, not the angle. So I missed that.
Yeah, it's tricky. The invariant interval versus like the there is no invariant angle.
Yeah. So no, there's no problem here.
Okay, so
one suggestion that if you make similar equation, you could put the line number or equation number on the side of the paper, so we can refer to the line.
Yeah, that not a bad idea. I guess I should number these equations. But so this next part actually gets to our question of, well, is the angle theta lab larger or smaller than theta rest? And so as we've been talking about, there's like a uniform angular distribution in the rest frame. Like it should just be emitted in any direction. There's no preferred direction when the pion's at rest. And so since the angle is like less than pi over 2, it'll the boost will shift it toward the like positive x-axis. So, this equation here, the like arctangent equation, you can use it to actually plot out well, what is theta lab in terms of theta rest? And I went all the way up to like pi over 2, just about. I guess not all the way up to pi over 2, but it gets, the cosine of pi over 2, it blows up, or 1 over that blows up.
Mm-hmm.
So we can't actually get all the way to pi over 2. But
Yeah.
here's just plotting this equation with the arctangent. So we end up with what is theta lab going to be in terms of theta rest. And so we'll see for small theta rest, it's about the same. But as theta rest gets larger and larger, it's like theta lab takes a long time to grow. Like, see, by the time that this is 1 radian, this is still like 0.2 radians. You see what's going on here? Like, we're at like pi over 3 at this point is the angle in the rest frame. And this is like pi over 8 or something like that.
Yeah. So it grows a lot slower.
Yeah, it grows a lot slower for small angles, but then for larger angles, it ends up growing like it's asymptotic.
Yeah, this resembles a lot of the gamma factor plot. It's very similar. Probably because there is gamma factor in it.
Yeah. It's because we got this like 1 over beta gamma. Yeah, this term right here.
But like in terms of that equation, it seems that those beta coefficients will be only like a constant term there in the function, and it's more dependent on the cosine there and the theta rest.
Yeah. I mean, this is just like a pure function, like, of one variable. We could do a multivariable plot with, like, if we put beta from 0 to 1. But I think it would be mostly uninteresting because, like, the only values of beta that are interesting are values that are close to 1.
I just trying to think out loud, like, what does it mean? Like, because any direction in the rest frame is kind of on the same footing, right? That means that we can have those like big growing theta labs also.
Yeah, definitely. Yeah, we could have them emitted at pi over 2, or I mean close to pi over 2, just below it. But the issue is that if you want to do conservation of form momentum, then it turns out that would correspond to a very, very high energy photon. Like, we're talking gamma rays or something like that. So this sort of gets to the part that you're asking. So now we consider a beam of neutral pions, all with the same energy. In the rest frame, as we've been talking about, like there's no angular distribution; it's just uniform. So now it's asking, well, what is the angular distribution of photon energy? Or sorry, what is the distribution of energies in the lab frame? So it turns out that since let's go back up to this equation up here. So we got this, right? The energy in the lab frame in terms of just cosine theta rest. Do we recall this equation, or shall I? Okay, no questions. So this is the energy in the lab frame of the first photon, in terms of a bunch of given quantities, and then the theta rest. So we know that in the rest frame, there's no preferred angle. So, the photons are emitted uniformly in theta rest. But that also means that they're emitted uniformly in cosine of theta rest, right? So cosine goes from -1 to 1. And so if we have, isotropic emission at any particular angle, then we have isotropic, like, energy distribution from when cosine goes from -1 to 1. Does this make sense? Does this argument?
Yeah, of course.
Okay, so this is actually what I draw out as the plot, is that I just plug in, well, it's uniform in cosine theta rest because it just goes from -1 to 1. So we end up with just like a 1 minus beta term and a 1 plus beta, but it ends up being a purely uniform distribution there. And my argument is just that we were able to write the energy in the lab frame in terms of the cosine of theta rest. And because we're uniform in theta rest, then we'd be uniform on the interval -1 to 1 for cosine theta rest.
And why do you have a straight line there? I mean, I have thought that depending on the cosine value, you will have different values for the energy. Or it's a probability for any energy.
Yeah. So I have it up here. I guess it's not as explicit. It's the probability of getting a photon of energy.
So it's, okay, then that's just depicting the uniform distribution. Okay. Mm-hmm.
Yep, so it's uniform between the minimum energy and the maximum energy. And so the minimum energy, I'll go back to this equation. So the minimum energy is going to be when cosine theta rest is a -1.
Yeah.
So this inner term here will be 1 minus beta. And the maximum energy will be when cosine theta is 1. So we get a 1 plus beta.
Yeah, true. Mm-hmm.
So that's what I have here. It's like the minimum and the maximum. The difference is just a sign on the beta. Okay, I know this is a lot, but let's just kind of summarize. So we have like a neutral pion with energy like 0.75 GeV, and it decays into 2 photons. We made some assumptions to make the calculations a bit easier, but just from being given the energy of the pion in the lab frame, we were able to calculate the beta factor. And then knowing the beta factor and an inverse Lorentz transformation, we were able to get the energy of that photon in the lab frame in terms of the angle that it was emitted in the rest frame. And then we go through and determine that angle in the lab frame in terms of the angle in the rest frame, and we found that it's actually much smaller. So following that, we just plotted what the lab frame angle would be in terms of the rest frame angle, and found that it grows very little, all the way up to about one radian, and then it sort of approaches pi/2 asymptotically. And finally, using some arguments about the uniform distribution in the rest frame, we were able to actually determine the probability of detecting a photon of energy E. And we determined that it was uniform between the minimum and maximum possible values. So I know that was long and probably a little unfamiliar, but I appreciate you guys for listening.
Yeah, thank you very much. It was really interesting.
Good lesson. Yeah.
I wanted to ask one more question about the angles. So, from that graph of the dependency of theta lab on the theta rest, there could be situation, if correct me if I'm wrong, there could be a situation when theta lab is bigger than theta rest, right?
Definitely. Yeah, because you can see here, like we already hit like 1.5 radians. We already hit that before we reach 1.5 radians here.
I'm just trying to think, like, you have said that it means that this photon is having like a really big energy, right?
Yeah, so that would just be for conservation of energy and momentum. If it's emitted like near perpendicular to the initial direction of travel for the pion, if it's emitted like near perpendicular to that, there's very little momentum along the x direction left over. So you need a very high energy photon to keep that x momentum. Does that make sense?
And the vertical axis is the time axis or space, like the different space axis.
So I'm just saying, like, the pion is traveling in this direction, and if it decays into two photons and they make a very large angle, let's see, even larger angle, right? So like here's the vertical, and here's the x direction. So if this is a pion, and these are two photons, then in order for this component of the like x momentum, which would be like e photon cosine of theta lab, that must be equal to, you know, like the original magnitude of the pion's momentum.
Yeah, and that means that it should be really long in terms of.
Yeah, so like as theta lab goes toward pi over 2, the cosine goes towards 0.
Yeah.
Right, so the energy of the photon would have to be huge.
So I was thinking about like maybe low energy pion, something like that, and basically it means that it can emit, like just from a probabilistic point of view, it can emit like high energy photons, right?
I'm thinking, just a moment.
Or do they distribute with a wide angle if the pion energy is low? So we can expect it to be wide angle.
Yeah, so I think, to answer your question, Slava, I think that you're probably just imposing conservation of momentum, but the thing is you need to impose conservation of energy and momentum, which is conservation of 4 momentum. So I think that, like, if you only impose one of those conditions, then yeah, you can get these situations where it's like, oh, I should expect to see very large photons. But the energies of the 2 photons have to add up to the mass of the pion in the rest frame.
Yeah. So basically that angle, depends on both, like on momentum and energy.
Yeah, exactly. And so that's what we get from the Lorentz transformation. That's how we get that dependence on the angle.
Yeah, and for example, if you want like a really high angles, we need a high energy pion.
Right. Yeah, a 0.75 GeV is actually not that large, right? I mean, like the beams at the Large Hadron Collider are on the TeV scale. So, I mean, we're talking 3 orders of magnitude here.
Yeah.
So even this like 0.75 GeV Pion, that's not as high energy as like what we talk about at Large Hadron Collider or anything. It's like 1,000th of the energy of what we talk about at the collider.
Okay, thanks. I got it.
Different kind of question. Is this spontaneous like split what we are talking about here?